On dot paper from the other side, and create as many different squares with areas from 1 to 100 as possible. On the grid, a horizontal or vertical segment joining two dots has a length of 1. Each of the vertices of the square must be on a dot. Find the area of each square you made and label each square with its area. Complete the table below using the squares created. Alright, now as it turns out, we're actually not too concerned with that chart or graph or grid, whatever you want to call it. But what we'll do is we'll look at this, and specifically the area on these. So for example, let's say that I had a square up in here, like these, and then this has a side length of 1, okay? Well, if I have a side length of 1, what would the area be? 2, of course. Not 2. It is not 2.
It is 3.
Because the other side length is 1. And to find the area of a square, we do the side length times the side length. And 1 times 1 is 1. Alright, next up, let's make this a little bit bigger square now, up in the count. So, it's just twice as big about, something like these. Well, now I've got side length of 2 for these sides. Well, if I had a side length of 2, what would the area be on these? Yeah, then I've got 2 times 2, which is 4. Alright, so let's say that this had a side length of 3 up in the count. Well, then the area would be 3 times 3. So the side length is 3, then the area is 9er. Okay. Now, we just got finished with the unit with the exponents. So, for example, if I just moved on to the side length of 4, how would I find the area? It'd be multiplied by itself, and I would get an area of 16 square units. Now, we should be able to fill in all the rest of these. Alright, so we'll go all the way to 17. Now again, if we wanted to write this a little bit different, I could do 5 squared, which is 25, right? Count. And then the next one would be 6 squared, which is 36. And then we'd have 7 squared, which is 49er. Yeah, so even though they said just to do from side lengths from 1 to 10, we're doing up to 17 just because we had all those spaces up in count. Now, we don't need to draw all of these because we can see the pattern up in count. We're just squaring the side length to get the area of these. So, if I wanted to find the area of a square, and we got to be careful on this, all right? Because if you do s times s, then it's going to spell a bad word. So, we've got to do s squared on this, okay? So just be very careful on it, these. Parents don't like it when you write swear words on your papers. It's very bad. Then I have to show it to the principal as well, and then he doesn't like it either. So just be very careful. Don't expand that s squared. But this would be the formula for finding the area. The question is, let's say that I gave you an area that was 25, and I said, I need you to find the side length up in here. Well, how would we find that side length? That is what we need to figure out today. Alright, so that takes us to number 4 up in here. They've given us some area. I don't know why it's number 4, by the way, but I guess that's what it is. And we got to find the side length of these. Now, we could use the previous chart, but we may not need to. For example, if I had a nice square up in here, like this one, and I said that this length was 1 and this length was 1, so we do have a square. Well, not 1 and 1, I'm sorry. The area they gave us is 1. So if I said, hey, the area of this square is 1, or 1 square unit, then what would be the side length?
1.
Well, we know that 1 times 1 is 1, so the side length would be 1. And we would fill that into the table. Yeah, some of you guys said we are getting into square roots, which is what this is. And some of you guys don't know where that button is on the calculator, which we will help you find later on. But for now, we should be able to fill in all of these values without a calculator, even if we just use the table on the previous page. So if I go down up in here, I'm going to use the same square, but now they've changed the area to 9 square units. So in other words, something multiplied by itself is 9.
3.
Yep, and that would be 3. 3 times 3 is 9er. So we know that that side length is 3. Length of 5. Alright, so this one gave us the side length of 5. This one's actually a lot easier than those other ones. So 5 times 5 would be 25 square units. So I got a 25 up and count. Alright, now this one is the one where we got to look and be very careful with the values that we use, because now it is an area of 2 square units. So what two numbers multiply to give us 2? Well, again, we could look at some values. 1 times 1 is 1. That's close. 2 times 2 is 4. That's a little bit too high, so we could try like 1.3
Yeah, it's like 1.4.
times 1.3. Yeah, well, hold on a second. We're getting to that, all right? Well, that's close. That would give us 1.69er. So what about 1.4? 1.4 times 1.4 is 1.96. That's pretty close, but it's not exact.
5.
So the problem is if we went on down the line on this, we could get extremely close to 2, but we would probably never get actual 2. And that's where we get these inverse operations, okay? So let's discuss inverse operations. Alright, so far we've learned several operations, such as addition, subtraction, multiply, and divided. Well, inverse ops for all 4 of these, we should be able to know by now. Inverse to addition would be subtraction. So inverse to subtraction is addition. Then inverse to multiplication is division. And inverse to division is multiplication. But now we've got these exponents up in count. So if I look at a to the power of, let's say, x, so that's an exponent, then I should have an inverse op. Let's specifically, instead of using x for now, let's use 2, because we're looking at squares up in count. So let's change that to a 2. Well, that would give us the inverse op of square roots of a, okay? So a square root as well is kind of like division of exponents, but since you guys didn't like that stuff, we'll not discuss that in too much detail right now. So what this means is on the calculator we got to find this symbol, which is called a radical. Some of you guys maybe on a button like this. Some of you guys may have to push the second button to get to this button, but in order to find that value, I've got a 2 as my area, but what I want is the side length. So what we got to do, right, we know that the area is the side length squared, but we've got an area of 2. Now inverse operations undo operations, specifically in this case, an exponent. So what this means is if I were solving equations using principles of equality, I would square root both sides, and then I would have just the s, and I would have the square root of 2. So the length of the side of an area of a square with area 2 would be square root of 2. Now some of you guys did put this in the calculator and you found the decimal. Unfortunately, these are what we call irrational numbers, which no one usually remembers anything about. It just means that the decimal never repeats or terminates ever. So if this is the case, then the area with the square with the 5, an area of a square with an area of 5 has a side length of square root of 5. So again, I'm going to go back to this, right? My area is the side length but squared. In this case, though, they gave us an area of 5. And to get rid of the square so that I have just the side length, I'm going to square root that garbage. But for an equation like we have right now, if I do it to one side, I got to do it to the other side as well. So my side length is simply the square root of 5, which is an irrational number, and that's how we get that value. So I'm just using the equation on all of these to solve them. Now some of you guys know, I'm looking now at the area of 100 radical. So again, I'm just going to go in there and replace 5 with 100 and see what that equals. So I got the square root of 100 would be the side length. And the square root of 100, if I put that in the calculator, would be 10.
What?
Now we can see that on the previous table, when we had a side length, a square with a side length of 10, we found that the area was 100 because it's 10 times 10. But then we run into these types where the side length is a square root. Now if I look at the formula, area is the side length squared. But now I've got a side length that is square root of 13. Now remember, a square root and a square, or the power of 2, cancel each other out. So I'm just left with 13 as the area. So this area right here is 13. Another way we can look at this, and you could put this into a calculator, is that the area, right, is the side length times the side length. So I can say my side length is 13, and then I can multiply it by itself, 13. And if I put this into a calculator, I should get just 13 right here. All right, then you guys take a moment and figure out what the area is with the side length of 20 here at the bottom. All right, so the area would just be 20 times 20, which is 400. Bam. So up in here, 5, on A they gave us the side length, and the missing measure right here is the area. Well, the area is side length squared, but we can see that the side length is 11. So I replace my side length with 11, and I get an area of 121. Now that was centimeters, by the way. So I can put centimeters squared. Bam. There's my missing measure. All right, B, this one is the area, though. And since area is the side length squared, but of course we can see the area is 16 meters squared. So when we label this, the side length will be in meters. And how do I solve with these? Well, I can say to myself, one number multiplied by itself is 16, and some of you guys know that. The rest of us may need to use radicals on it, these. So I'm going to square root both of them. So the square root and the square cancel each other out, and I'm left with my side length. Square root of 16, as it turns out, is 4. So the answer would be 4 meters. Complete the following sentences. Provide examples to support your statement. A perfect square is created when the side length is a whole value. For example, if we had a side length that was 8, then a perfect square would be 8 squared, which is 64. All right, to find the area of a square when given the side length of a square, all you must do is simply square the side length. All right, what about to find the side length of a square given the area of a square? All we're going to do is square root the area. All right, so another example on number 7 right here. So if they gave us a side length, it's kind of that first one as well. If the side length were 7, then the area would be 7 squared, which would be 49. And again, we can say units squared if we want. On the other hand, if they gave us the area, which let's say was 144 units squared, then the side length would be the square root of 144, which would give us 12 units. All right, so let's simplify these. All we've got to do in the calculator, now for some of you guys, here's what you got to do. You got to push the second button. This is usually for TI 30s. Then you've got to find this button, x squared. That will give you the square root, and then you punch in your number, 36, and then you're going to push the equals button. Bam. You should get 6. These do not have units. Therefore, we don't need to label these with any type of units. Also a good point. This would be like asking what the side length is if the area of a square was 36. Yep. Yeah, good point. So D, just below, if I had an area of a square that was 1, what would the side lengths be? We've done several rules, right? Of 1. Alright, knowing that.
The square root of 9.
So, what number multiplied by itself is 625? Yeah, it was 25, right?
Let me check.
Alright, who can tell us the answer to B? 11. C. I.
25. 15.
We can't see I.
Next one is
It's on your paper.
7.
Let's try H.
15.
Very good. What about F?
7.
And finally E.
10.
Nice.
Yourself.
Now again, we can find these just using a calculator. I would look at the charts just because I'm already up here, but
Wait, so G
it only
was
goes up to 25. Now as it turns out, we need to be able to find the lengths of lines, which are not like the squares that we're used to. We'll see it on the grid. So in the previous sections, we learned how to simplify square roots for perfect squares. For example, the square root of 36 is 6. That's great. What about square roots of non-perfect squares? We did look at the square root of 5. And what about the square root of 8 or the square root of 147? Let's go ahead and take a look at the D. In terms of the lengths of these lines, A through F without using a ruler, so we're not going to use a ruler. Besides, these are irrational.
Why do you have
No.
a scientific calculator?
Write your answers in the space provided below each grid. I'm not going to use that space because I got this grid right here.
Switch to a scientific.
All right, so right here, we have this line, and we got to find the length of a D's. Now, it's important to remember that we've been comparing squares, so I could connect these points and say, well, there's the side length of that square. Okay, but again, we just don't know what that is. So as it turns out, we may need to use some sloppage. This is not always the case, all right? But for now, it's just to help you understand what to do when you see the homework, okay? So for example, the sloppage is up 1 to the right 1. Like these. No. You're close though. So what I'm going to do is, I'm going to take the square root of both of these. I'm going to add them, but I'm going to square them like these. So that means that I've got the square root. If I use the order of operations, I've got 1 plus a 1. And then it's the square root of 2. Right there. See that? So A, side length of A is the square root of 2. Alright, now B, some of you guys noticed that we got one of these square roots of 2. That's the square root of 2. And then I got another square root of 2. So B has the length of square root of 2 plus the square root of 2, because it's the same as A. But, not that everyone remembers this, but this is, we can simplify addition with multiplication. So, as it turns out, we got 2 groups of square root of 2. Bam. But there's another way to look at this that you guys are going to hate. So let's look at this a different way. And we'll see that it's the same thing. But if I made a square up in here, like these, okay, and I use a good old sloppage, so I go up 2, then to the right 2, then I've got the square root of 2 squared plus the other 2 squared. So that's 4 plus 4, which is the square root of 8. So as it turns out, this 2 times the square root of 2 is also the square root of 8. All right, so C, this line C, that's the square root of 2 right here. This is also another square root of 2 and another square root of 2. If I combine them, Then I got the square root of 2 plus the square root of 2 plus the square root of 2. But I can simplify this. I've got 3 of these, 3 groups of the square root of 2. All right, very good. D. Here we've got 1, 2, 3, 4 of these square roots of 2.
Why is it 2? Wait.
All right, let me look at this a different way with you guys real quick. All right, I do want to look at this a little bit differently. So if I look at this line radicale, and I said I want to find the side length, that length of that line. So again, we could make a square radicale like this, right? Okay, well that's a square whether you like it or not, sorry. So
Diamond?
it's a square, it's just been tilted. All right.
Oh my gosh, it's
Now here's the thing is,
It's a rock.
if I told you the area of this thing, could you find the side length?
Yes.
Yeah, sure you could, right?
yeah, it's
Because you know that the area is the side length squared. So if I wanted the side length, I would just square root the area, right? So if I can find the area, then I should be able to find the side length. So here's what we can do is find the x. We can find the area of this square. Okay. Keegan? What we're going to do is I'm going to split this up into 4 parts. Now here's what I have. I got 4 identical triangles in this square. So if I can find the area of one of these, then I'm good. Now, you guys don't remember this, but the area of a triangle is half of the base times the height. Oh, that's a B. Let's use an H on that. Well, the base on this is 1 unit, and the height is 1 unit. So the area of one of these triangles is 1/2 times 1 times 1. So that's 1/2 right there. Well, that means all of these have an area of 1/2. So overall, in these. All right, so we can look at these, and we can see, or we should be able to see, that these two give us one of these squares radicale. And then these two radicale give us another square radicale. Or if I add them, it just gives me a value of 2. So my area is 2. So I can take the square root of 2. And that would be the side length, square root of 2. All right. So let's look at these. On E, we need to find its length. So I'm going to go 1. I'm going to go down 1 and then to the right 3. Now the side length, E, let's actually use E on this. The side length of E is going to be the square root. Now I've got that -1 as my stoppage. And I've got another side length of 3. All I'm going to do is square those and then add them together. Now notice I've got -1 in parentheses. That's because when I square that, it's going to make that a positive. And then 3 squared is a positive 9er. So I get square root of 1 plus 9er, which is the square root of 10. All right, I'm just going to show you this one more way, and then we'll move on to the next one and be done with this page. So on this one, if I wanted to make a square on these, let me use a different color on that. So I would have this line, and then 1 and 3, and then these. There's my square. Now again, I could split this up using all the dots and some triangles and stuff. Like these.
Mr. Sal, you're tripping me out. We should have.
Now if we look at this has an area of 1, 1, 1, and 1. And if we look at this part right here, this combines to be 1.
Whoa.
If we just manipulated those.
Oh, goodness.
These, well, hold on, let me check. Where am I at?
D grade.
Yeah, these ones. These ones combine to give us another area of 1.
Oh, that's
What the heck?
cool.
And then the upper middle one.
And then this one's radical. Give me an area of 1.
Well, if you combine 2 of those,
So it's 10.
Alright, then I've got another one, which I'm going to do this one a different color. If I look at these, one, and if I were to combine it with these, that would give me another 1. And then if I were to combine these with these, I would have another 1. And then if I were to combine these, where am I at? With it, should be a little bit more than it is. Yeah, so if I combine these with these ones, all the rest of it, then I should get 1 more. That gives me an area of 10. So if I had an area of 10, then the side length would be the square root of 10. So yeah, most people don't use this method because it's kind of hard to tell how these are going to fit into each other. And if you guys find the area, I'm sorry, not the area, but the side length, length F. Alright, let's go ahead and get started on this one. So, if I use sloppage, right, I'm going to take the square root, I'm going to square both sides and then add them together. So, I'm going to use sloppage. I went down 2, so I got a negative 2 radical. And then this one looks like it's 6. So, this gives me the square root of 4 and 36, which I'm adding together, which would then give me the square root of 40. So this is one of the answers. Another way to look at this is, remember the last one had a sloppage of 1 and 3, but this one is 2 of those. So some of you guys may have said 2 and the square root of 10. Well, it's 2. 10, that's better.